Hello and welcome to our lesson on the precise definition of a limit. This is going to be from section 2.4 in our calculus course. Let's get started. We have the precise definition of limit. It says, let f be a function defined on some open interval that contains the number a. Right there it says a. Except possibly at a itself, then we say that the limit of f of x as x approaches a is L. And then we've seen this before. This is our limit notation. This is going to be true if for every epsilon greater than 0, there is a number delta greater than 0 such that, and then let me zoom in on this part. This is the important part, such that, and then look what this says. X minus a, the absolute value of that, it has to be less than delta. What the freak does that even mean? That means that the distance of any x that you choose, the distance from that x to a, if it's less than delta, then the distance from the function value, right, based on whatever x you're at, the distance from the function value to the limit is guaranteed to be less than epsilon. So this is what the precise definition of limit says. So again, this limit is going to exist if you tell me how close you want to be to L. Epsilon is your distance away from L. I'll tell you how close you need to be to A to guarantee that you're within epsilon of L. So one more time, there it is. You can screenshot that or pause for a second to focus on what that says, and then we're going to look at an example. All right, so before we look at an example, let's look at a graphical representation of what this delta epsilon definition of limit says. Okay, let's consider this limit. Let's say we want the limit of this function right here. We're going to just use f of x to denote that function as x approaches 1. Now we can see that as x approaches 1, y approaches 2. We can see that that limit is 2. But what the delta epsilon definition says is this. It says if you'll tell me how close you want to be to your limit, that whatever epsilon is, it could be 0.5, it could be 0.005, it could be any number. Epsilon is like the tolerance around your limit. If you tell me how close you need to be to L, then what we can do is bring that over and down, and bring this over and down. And that is a very wide gap. But what that means is, it means that we're going to have x's, okay? We would call this x1 and x2, and we're concerned with as we approach 1. Now the distances, like the distance from 1 to this x over here, that we could call that delta 1, and then the distance from this x to 1 here, we could call that delta 2. Whichever one of those is smaller would be our choice for delta. That says this, okay? If you're within delta, whatever it is, of A, what that's going to do is that's going to guarantee that you're within epsilon of L. And then if you say, well, I need epsilon to be smaller, like if you need to get closer to L, then all I'm going to do is say, well, then you need to stay closer to A. And then that gives us a new delta. So no matter what you tell me epsilon is, I should be able to give you a delta that guarantees that if you stay within that distance of A, I can guarantee that you're going to be within epsilon of L. That's the best I can do for giving you an explanation of what this precise definition of limit says. Now let's look at an example and see how it works. All right, so here we go. We have prove the limit as x approaches 2 of the function 3x plus 1 is 7. We're going to prove that using the delta epsilon definition of limit. But I first want to illustrate how we know that automatically. Remember, we've already covered that you can do a limit with direct substitution, provided that you don't get an undefined situation. So I can simply evaluate this function at 2, and we can see that it is going to approach 7 because the function value is 7. So as we approach 2, the y's are going to approach 7. So now we're going to illustrate that with the delta epsilon technique, the delta epsilon definition of limit. Here's how it works. You're going to start and say, okay, given an epsilon greater than 0. Now remember, epsilon is you telling me how close you want to be to L. Given an epsilon, or a distance from L, we can choose a delta that will guarantee that we stay within epsilon of L. Now, we're not going to know what delta is automatically. And then we suppose that the distance from any x to a, that's what this means. The absolute value of x minus a is the distance from x to a. If you choose an x that's close enough to a so that it's within delta, then we should be able to show that you're within epsilon of L. All right, so then here's how we figure out what delta is. The check works like this, okay? Our a in this case is 2. A is what x approaches. We start off with what we want to get to, and we want to get to a point where we show that f of x minus L is less than epsilon. Okay, if I scroll back up, this is the proof, okay? Given a delta, then we should be able to show this part, that f of x minus L is less than epsilon. So we start with where we want to end up and work to where we begin. Okay, so what is our f of x? Our f of x is 3x plus 1 minus L, which in this case we know is 7. We want to show that that is less than epsilon. Remember, this is where you would end your proof to prove the delta epsilon definition of limit. So we're going to start here and work backwards until we arrive at the supposed step. All right, so combine like terms. We're going to have 3x minus 6 less than epsilon. I can then factor out a 3, leaving me 3 times x minus 2, still within the absolute value. And then there is a property of absolute value that says factors can be separated into their own absolute value. So then I would end up with this step. The absolute value of 3 times the absolute value of x minus 2. But what is the absolute value of 3? Well, that's just 3. X minus 2 less than epsilon. And then if I divide everybody by 3, that's still going to be 0. And really all this part says is that your epsilon or delta is positive. That's all this part says. These cancel. Leaves me x minus 2 less than epsilon over 3. Now this is where we need to be. Notice that this is now the supposed step. This is what we suppose, and remember that we need to figure out what delta needs to be. Well, this tells me that delta needs to be epsilon over 3. And remember, epsilon is what you're requiring. Somebody's going to give you an epsilon and say, I need you to be this close to L. And then you should be able to take that value of epsilon and say, okay, well, delta needs to be, in this case, epsilon divided by 3. And then I can go back and give you a delta. Now, all of this is not the proof. All of this is determining what we need to let delta be. And we have now determined that delta needs to be epsilon over 3 in order to make the proof work. Okay, so then here comes the proof. It's basically what we did already. You always start the proof with given epsilon greater than 0. And then you're going to tell that person, okay, well then I need you to choose delta to be your epsilon over 3. If you choose delta to be that, then we can suppose that any x you choose, as long as it's within a distance of delta, right? I've told you what delta needs to be here. As long as you choose an x that's within delta of 2, then we're going to show that you're going to arrive at the absolute value of f of x minus L less than epsilon. All right, here we go. Showing, this is the proof. So we're going to say absolute value of x minus 2 less than, and we're going to replace delta with epsilon over 3. And then we're going to multiply through by 3. So multiply by 3 all the way through. 0 times 3 is 0. This is going to be 3 times absolute value of x minus 2. And those are going to cancel, leaving me epsilon. Okay, now, since this 3 is positive, I can go ahead and bring it into the absolute value. Multiplying that times a positive is not going to change that value. So then we have 3 less than, doing the distributive property gives us the absolute value of 3x minus 6 less than epsilon, and then I can break negative 6 down into positive 1 and minus 7. And now do you see that we're where we need to be? That now, again, if we reiterate what this is saying, it's saying if you will choose a delta to be epsilon divided by 3, then I can guarantee you that the function value, based on the x you chose, the function value will be a distance away from your limit that is less than epsilon. You will be within tolerance of your limit. And since this is the end of the proof, normally we put some kind of notation to indicate the proof is over. I've seen double slash, I've seen a lot of things. So I use the double slash to indicate we're done with the proof. And that is my attempt at showing you how not only the delta epsilon definition works, but how to actually find your delta and show that the limit is what they say through the delta epsilon definition of limit. And I could do more examples, but what I'm going to do is I'm going to let you go scour YouTube and maybe scour the internet. If you want to see more examples, if you want to see other people give their approach to this problem, by all means take a look at it, because I'm not so egocentric that I think that I am going to be able to explain this to everybody. You go look. If this doesn't make sense, you go find some examples and find somebody that does make sense. Okay, so that's going to do it for this video. If you have any questions or comments about anything covered in the video, please feel free to leave those in the comment section below, or you can text me. And thanks for watching.